Alright, welcome back. This is my favorite series, the Wild Networking series. Currently I'm reading the RFC on BGP, but I will be done with that very, very soon, so let's waste no time. This is Phase 3, Route Dissemination. The Phase 3 decision function is invoked in completion of Phase 2, or when any of the following events occur: when routes in the loc rib to local destinations have changed, when locally generated routes learned by means outside of BGP have changed, when a new BGP speaker connection has been established. The Phase 3 function is a separate process that completes when it has no further work to do. The Phase 3 routing decision function is blocked from running while the Phase 2 decision function is in process. All routes in the loc RIB are processed into ADJ-RIBS OUT according to configured policy. This policy may include a route in the loc RIB from being installed in a particular ADJ-RIB-OUT. A route shall not be installed in the ADJ-RIB OUT unless the destination and next hop described by this route may be forwarded appropriately by the routing table. If a route in the loc RIB is excluded from a particular ADJ-RIB OUT, the previously advertised route in that ADJ-RIB OUT must be withdrawn from service by means of an update message, C9.2. And just as a clarify, this is the adjacent routing information base for out. There's also one for in, but in the Juniper implementation at least, this is just the one for in and out is just shown in one table, but different vendors do it different ways. I think the most common way is to just have the out and the in just show up in the routing table with extra info attached to it and not be its own tables, although this RFC does outline it as if they were two completely separate tables, but it certainly does not have to be implemented that way on a device. Routing and aggregation. Route aggregation and information reduction techniques, see section 9.2.2.1, may optionally be applied. Any local policy that results in routes being added to an ADJ-RIB OUT without also being added to the local BGP speakers forwarding table is outside the scope of this document. When the updating of the ADJ-RIBS OUT and the routing table is complete, the local BGP speaker runs the update send process of 9.2. Overlapping routes. A BGP speaker may transmit routes with overlapping network layer reachability information, NLRI, to another BGP speaker. NLRI overlap occurs when a set of destinations are identified in non-matching multiple routes. Because BGP encodes NLRI using IP prefixes, overlap will always exhibit subset relationships. A route describing a smaller set of destinations along your prefix is said to have more specific than a route describing a larger set of destinations, a shorter prefix, which will have more host addresses available per prefix. A route describing a smaller set of destinations or subnets or networks that has a longer prefix has a smaller number of hosts. Similarly, a route describing a larger set of destinations is said to be less specific than a route describing a smaller set of destinations. So, yeah, it may seem, and I think that makes intuitive sense. A /32 is going to be considered more specific than a /8. No, sorry. Actually, I got that completely wrong. wait. So, yeah, so this is a route describing a set of destinations. So a route describing a larger set of destinations has a longer prefix. So if you have a /32 versus a /30, the /32 is the longer prefix portion, and in fact it's the whole portion, it's every bit set to a 1. So that's considered more specific. So it describes a shorter set of destinations. Yeah, I think basically you can swap out the term set of destinations for hosts. That's what they're talking about. Because if you have a /24, you've got a whole octet that can be used for a set of destinations, except for the broadcast and the network address. So you have more destinations than a /30, where you only have 2 host IPs and then 2 IPs for one for the network address, one for the broadcast address. So yeah, it makes more sense if you think of it that way. What they mean by set of destinations is number of host IPs possible. The precedence relationship effectively decomposes less specific routes into 2 parts: a set of destinations described only by the less specific route, and a set of destinations described by the overlap of the less specific and more specific routes. The set of destinations described by the overlap represents a portion of the less specific route that is feasible but is not currently in use. If a more specific route is later withdrawn, the set of destinations described by the overlap will still be reachable using the less specific route. If a BGP speaker receives overlapping routes, the decision process must consider both routes based on the configured acceptance policy. If both a less and a more specific route are accepted, then the decision process must install in locRIB either both the less and more specific routes, or aggregate the 2 routes and install in locRIB the aggregated route, provided that both routes have the same value of the next hop attribute. If a BGP speaker chooses to aggregate, then it should either include all ASs used to form the aggregate in an AS set, or add the atomic aggregate attribute to the route. This attribute is now primarily informational. With the elimination of IP routing protocols that do not support classless routing, and the elimination of router and host implementations that do not support classless routing, there is no longer a need to de-aggregate. Routes should not be de-aggregated. In particular, a route that carries the atomic aggregate attribute must not be de-aggregated. That is, the NLRI of this route cannot be more specific. Forwarding along such a route does not guarantee that IP packets will actually traverse only ASs listed in the AS path attribute of the route. 9.2 Update Send Process. The update send process is responsible for advertising update messages to all peers. For example, it distributes the routes chosen by the decision process to other BGP speakers, which may be located in either the same autonomous system or in a neighboring autonomous system. When a BGP speaker receives an update message from an internal peer, the receiving BGP speaker shall not redistribute the routing information contained in that update message to the other internal peers. unless the speaker acts as a BGP route reflector. As part of Phase 3 of the route selection process, the BGP speaker has updated its ADJ-RIBS OUT. All newly installed routes and all newly unfeasible routes for which there is no replacement route shall be advertised to its peers by means of an update message. A BGP speaker should not advertise a given feasible BGP route from its ADJ-RIB-OUT if it would produce an update message containing the same BGP route as was previously advertised. Any routes in the loc RIB marked as unfeasible shall be removed. Changes to the reachable destinations within its own autonomous system shall also be advertised in an update message. If, due to the limits on the max size of an update message, see Section 4, a single route doesn't fit into the message, the BGP speaker must not advertise the route to its peers and may choose to log an error locally. 9.2.1 Controlling routing traffic overhead. The BGP protocol constrains the amount of routing traffic, that is, update messages, in order to limit both the link bandwidth needed to advertise update messages and the processing power needed by the decision process to digest the information contained in the update messages. Frequency of route advertisement. The parameter min route advertisement interval timer determines the minimum amount of time that must elapse between an advertisement and or withdrawal of routes to a particular destination via a BGP speaker to appear. This rate limiting procedure applies on a per destination basis, although the value of min route advertisement interval timer is set on a per BGP peer basis. 2. Update messages sent by a BGP speaker to a peer that advertise feasible routes and or withdrawal of unfeasible routes to some common set of destinations must be separated by at least min route advertisement interval timer. This can only be achieved by keeping a separate timer for each common set of destinations. This would be unwarranted overhead. Any technique that ensures that the interval between two update messages sent from a BGP speaker to a peer that advertise feasible routes and or withdrawal of unfeasible routes to some common set of destinations will be at least min route advertisement interval timer, and will also ensure that a constant upper bound on the interval is acceptable. Since fast convergence is needed within an autonomous system, either A, the min route advertisement interval timer used for internal peers should be shorter than the min route advertisement interval timer used for external peers, or B, the procedure described in this section should not apply to routes sent to internal peers. They're missing a D. This procedure does not limit the rate of route selection, but only the rate of route advertisement. If new routes are selected multiple times while awaiting the expiration of min route advertisement interval timer, the last route selected shall be advertised at the end of min route advertisement interval timer. Frequency of route origination. The parameter min AS origination interval timer determines the minimum amount of time that must elapse between successive advertisements of update messages that report changes within the advertising BGP speaker's own autonomous systems. Efficient organization of routing information. Having selected the routing information it will advertise, a BGP speaker may avail itself of several methods to organize this information in an efficient manner. Information reduction. Information reduction may imply a reduction in granularity of policy control. After information is collapsed, the same policies will apply to all destinations and paths in the equivalence class. The decision process may optionally reduce the amount of information that it will place in the ADJ RIBS OUT by any of the following methods. Method A, network layer reachability information. Destination IP addresses can be represented as IP address prefixes. In cases where there is a correspondence between the address structure and the systems under control of an autonomous system administrator, it will be possible to reduce the size of the NLRI carried in the update messages. Method B, AS paths. AS path information can be represented as ordered AS sequences or unordered AS sets. AS sets are used in the route aggregation algorithm described in section 9.2.2.2. They reduce the size of the AS path information by listing each AS number only once, regardless of how many times it may have appeared in multiple AS paths that were aggregated. An AS set implies that the destinations listed in the NLRI can be reached through paths that traverse at least some of the constituent autonomous systems. AS sets provide sufficient information to avoid routing information looping. However, their use may prune potentially feasible paths because such paths are no longer listed individually in the form of AS sequences. In practice, this is not likely to be a problem because once an IP packet arrives at the edge of a group of autonomous systems, the BGP speaker is likely to have more detailed path information and can distinguish individual paths from destinations. Aggregating routing information. Aggregation is the process of combining the characteristics of several different routes in such a way that a single route can be advertised. Aggregation can occur as part of the decision process to reduce the amount of routing information that will be placed in the ADJ RIBS OUT. Aggregation reduces the amount of information that a BGP speaker must store and exchange with other BGP speakers. Routes can be aggregated by applying the following procedure separately to path attributes of the same type and to the network layer reachability information. Routes that have different multi-exit discriminator attributes shall not be aggregated. If the aggregated route has an AS set as the first element in its AS path attribute, then the router that originates the route should not advertise the multi-exit discriminator attribute with this route. Path attributes that have different type codes cannot be aggregated together. Path attributes of the same type code may be aggregated according to the following rules. Next hop. When aggregating routes that have different next hop attributes, the next hop attribute of the aggregated route shall identify an interface on the BGP speaker that performs the aggregation. Origin attribute. If at least one route among routes that are aggregated has origin with the value incomplete, then the aggregated route must have the origin attribute with the value incomplete. Otherwise, if at least one route among routes that are aggregated has origin with the value EGP, then the aggregated route must have the origin attribute with the value EGP. In all other cases, and we've got an extra comma there, the value of the origin attribute of the aggregated route is IGP. AS path attribute. If routes to be aggregated have identical AS path attributes, then the aggregated route has the same AS path attribute as each individual route. For the purpose of aggregating AS path attributes, we model each AS within the AS path attribute as a tuple type value, where type identifies a type of the path segment the AS belongs to. For example, AS sequence AX set, and value identifies the AS number. If the routes to be aggregated have different AS path attributes, then the aggregated AS path attribute shall satisfy all of the following conditions. All tuples of type AS sequence in the aggregated AS path shall appear, and shall is the same as must, it's a synonym, in all of the AS paths in the initial set of routes to be aggregated. So you can read that as it must. All tuples of type AS sets in the aggregated AS path shall, and again, shall means must, it's the same word, appear in at least one of the AS paths in the initial set. They may appear as either AS set or AS sequence types. For any tuple X of type AS sequence in the aggregated AS path, which precedes tuple Y in the aggregated AS path, X precedes Y in each AS path in the initial set, which contains Y, regardless of the type of Y. No tuple of type AS set with the same value shall appear more than once in the aggregated AS path. Multiple tuples of type AS sequence with the same value may appear in the aggregated AS path only when adjacent to another tuple of the same type and value. An implementation may choose any algorithm that conforms to these rules. At a minimum, a conformant implementation shall, which again means must, be able to perform the following algorithm that meets all of the above conditions. Determine the longest leading sequence of tuples as defined above, common to all the AS path attributes of the routes to be aggregated. Make this sequence the leading sequence of the aggregated AS path attributes. Set the type of the rest of the tuples from the AS path attributes of the routes to be aggregated to AS set and append them to the aggregated AS path attributes. If the aggregated AS path has more than one tuple with the same value, regardless of tuple's type, eliminate all but one such tuple by deleting tuples of the type AS set from the aggregated AS path attribute. For each pair of adjacent tuples in the aggregated AS path, if both tuples have the same type, merge them together as long as doing so will not cause a segment with a length greater than 255 to be generated. Appendix F, section F.6 presents another algorithm that satisfies the conditions and allows for more complex policy configurations. Atomic aggregate. If at least one of the routes to be aggregated has atomic aggregate path attribute, then the aggregated route shall have this attribute as well. Aggregator. Any aggregator attributes from the routes to be aggregated must not be included in the aggregated route. The BGP speaker performing the route aggregation may attach a new aggregator attribute. See section 5.1.7. 9.3 Route selection criteria. Generally, additional rules for comparing routes among several alternatives are outside the scope of this document. There are two exceptions. If the local AS appears in the AS path of the new route being considered, then that new route cannot be viewed as better than any other route, provided that the speaker is configured to accept such routes. If such a route were ever used, a routing loop could result. In order to achieve a successful distributed operation, only routes with a likelihood of stability can be chosen. Thus, an AS should avoid using unstable routes, and it should not make rapid, spontaneous changes to its choice of routes. Quantifying the terms unstable and rapid from the previous sentence, will require experience, but the principle is clear. Routes that are unstable can be penalized. For example, using the procedures described in RFC 2439, so much earlier. Okay. BGP route flap damping. That's a big one. That's a big part of the JNCIE, and this is a proposed standard. One of the things I wanted to do. So if we just go to the main site here, datatracker.ietf.org, and then we go to documents. Okay, well, oh, here we go. Down here, RFC Editor. Now we can filter out the RFCs by their status. So what I wanted to do is go through all the internet standards, but I guess I'm surprised to see that BGP route damping is not an internet standard. It looks like it's a proposed standard. Huh. Now this is, I don't know what this is. This doesn't seem like an RFC. This is an IETF draft. Standards track. Yeah, I don't even know. But anyways, here's all the, this is kind of where I wanted to go at some point, is through all the standards. But of course, a lot of these are going to be completely irrelevant. But they're going to be better than. I'm going to learn a lot about Telnet if I do that, which doesn't seem like a good idea. I mean, I think Telnet can still be used to like test if a port's open or something like that. You don't have to use it to send passwords. Like, you don't have to, when you're using Telnet, you don't have to use it only for in-band management to a device where you have to send a password over it. You can use it for other things. But generally, like, I think it's a good idea to just disable Telnet and use SSH. Alright, so here's the proposed standard. So we're going to get damping here. Yeah, so we get BGP route flap damping. We get PGP. So these proposed standards look interesting. But yeah, you know what? I can just go through all of these. Yeah, communities are on here. I mean, this what I'm reading right here is the proposed standard. It's not even a standard. So the proposed standards almost seem like they're more, yeah, like OSPF and SSA areas are a proposed standard and not an actual standard. So I don't know what makes the cut between a proposed standard and an actual standard, but it seems to, yeah, like the specification for OSPF is proposed. Yeah, so that's weird to me. And then this is a draft standard. I don't know what that means too. It looks like TCP congestion control is a draft standard. Like, that does not seem like a draft standard. That seems like an actual standard. I'm not sure what they mean by the word draft. And then this is a current best practice. I'm not sure what mean by that either. I know there's things like RFC 69, which is just somebody like emailing them saying like to not include him anymore, include someone else. And then there's like avian like messenger carrier and like kind of joke RFCs. So if I see any of those on this list, I know I'm in the wrong place. But yeah, I think if I just stick to those 4 categories, I should be fine. It'd be nice if I could get like some design or architecture. Yeah, like this looks really interesting. A possible set of requirements for future routing architecture. That looks great. Yeah, cool. Multicast routing architecture, that looks interesting. Like, as I've mentioned many times before, I want to kind of start looking more for the kind of like more big picture. I want to get away from like small details that I'll never really actually use, and focus on labbing, and just like even like common simple like just a basic enterprise network, be able to set it up in the lab, reconfigure it, add switches. Just I want to get more I want to get more out of my lab, because I invested some money in that. It wasn't too bad, but I feel like I'm just not using it enough. It's like I've got a sports car, but yet I'm constantly biking. It's like, just take, so what are these? These are unknown. Oh, this is probably where you've got like, yeah, you've got so these are, oh yeah, these are unknown. So I wouldn't want to, all of these I can skip. I want to make sure I'm not kind of wasting my time on RFCs that aren't important, that aren't widely used in reference, which kind of puts into question what I'm doing here. But let's see here. So I'm on section 9.4. So I'm almost to the appendixes. The appendixes are going to be a lot of reading. So yep. So it looks like I'm really only done reading, because I'm not going to read the acknowledgments or the references here, even though some of these do look pretty interesting. It looks like this is informational, so I'm not sure if I were to do a series on RFCs by status, where I do a series of reading all the internet standards, all the draft standards, all the proposed standards, all the current best practices. Looks like I'd have to also read the informational in order to read about BGP security vulnerabilities, and that does sound like it would be really interesting. And it looks like a lot of these informational ones are like really like cutting edge. Like this is number 909. So let's see. What was it, 909 or 919? So this is 919, and these are informational. Okay, so this is 89. 4.9. So this is pretty pretty recent. But here, now that these this is a draft standard, yeah, this is pretty old. Proposed standard. Oh, this is actually pretty new. This is actually newer than this one. Current best practice. These are pretty new as well. Yeah, so exciting things to come. Might take me a while to get through all these, but yeah, I'll probably start with the informational because we've got a lot of good. Oh yeah, this is interesting too. Network coding for satellite systems. Satellite, I think, is the protocol police. Oh, yeah. That's interesting. I mean, how do you even police a protocol, though? Like, I guess that's the point of this, is to tell people how. Yeah, I don't know if I can join the protocol police, because the members of the protocol police must salute and ACK all network traffic from Daniel Kahn, Gilmore, Mallory Knodel, and Adrian Farwell, and I don't know if I can do that. Okay, but let's keep on track here. We're going to go back to section 9.4. Okay, I don't know why it's not taking me there. Okay, there we go. So it looks like we got about 11 more pages. I don't know if I can do that all today, but it's gonna be coming soon. So yeah, about at page, because I don't need to read about intellectual property, I don't need to read about copyright or any of the references. Yeah, so I can stop at like page 100. So I've got about 11 more pages to go. Alright, so let's waste no time. Originating Bgp routes. A Bgp speaker may originate Bgp routes by injecting routing information acquired by some other means, for example via an IGP, into Bgp. A Bgp speaker that originates Bgp routes assigns the degree of preference, for example according to local configuration, to these routes by passing them through the decision process. See section 9.1. These routes may also be distributed to other Bgp speakers within the local AS as part of the update process. See section 9.2. The decision of whether to distribute non-BGP acquired routes within an AS via BGP depends on the environment within the AS, for example, the type of IGP, and should be controlled via configuration. Bgp timers. BGP employs 5 timers. Connect retry timer, section 8. Hold timer, see section 4.2. Keep alive timer, see section 8. Min AS origination interval timer, see section 9.2.1.2, and min route advertisement interval timer, see section 9.2.1.1. 2 optional timers may be supported. Delay open timer, Idle hold timer by BGP, see Section 8. Section 8 describes their use. The full operation of these optional timers is outside the scope of this document. Connect retry time is a mandatory FSM, finite state machine attribute, that stores the initial value for the connect retry timer. The suggested default value for the connect retry time is 120 seconds. Hold time is a mandatory FSM attribute that stores the initial value for the hold timer. The suggested default value for the hold time is 90 seconds. During some portions of the state machine, see Section 8, the hold timer is set to a large value. The suggested default for this large value is 4 minutes. The keep alive time is a mandatory FSM attribute that stores the initial value for the keep alive timer. The suggested default value for the keep alive time is 1/3 of the hold time. The suggested default value for the min-AS origination interval timer is 15 seconds. The suggested default value for the min route advertisement interval timer on eBGP connections is 30 seconds. The suggested default value for the min route advertisement interval timer on iBGP connections is 5 seconds. And implementation of BGP must allow the hold timer to be configurable on a per peer basis and may allow the other timers to be configurable. To minimize the likelihood that the distribution of BGP messages by a given BGP speaker will contain peaks, jitter should be applied to the timers associated with min-AS origination interval timer, keep alive timer, min route advertisement interval timer, and connect retry timer. A given BGP speaker may apply the same jitter to each of these quantities, regardless of the destinations to which the updates are sent. That is, jitter need not be configured on a per peer basis. The suggested default amount of jitter shall be determined by multiplying the base value of the appropriate timer by a random factor, which is uniformly distributed in the range from 4/3 to 3/4 to 4/4. A new random value should be picked each time the timer is set. The range of the jitter's random value may be configurable. Now look at this, we got a free page here. So we're already on to page 92. I think I can finish it. In fact, you know what? I did finish it. We're on to the appendix now. So big round of applause for me. I read every single word of the original BGP RFC for BGP version 4. I didn't read it for version 3. I didn't read it for route damping. I didn't read it for, every little extra thing, which there is in RFC 4. But big accomplishment. I learned a lot about. I filled in a lot of gaps that I didn't know. I really didn't know how the MED value worked, and I have a really strong sense of that now. I really get that. The other thing is I didn't quite understand like how BGP routes were different from other routes. That they're truly just the data portion of a TCP packet, and NLRI really just is data. I think I have a bit of a better understanding of that now. The aggregate and the atomic aggregate attributes I also understand better, I think. I never really got those showing up until now. So but the biggest thing for me has been multi-exit discriminator. I spent a lot of time and effort on this, but it paid off just for what I learned about that. So let's try to close it out. We're going to read Appendix A, comparison with RFC 1771. So this must be BGP version, BGP version 4. So, wait, what? I'm confused. Oh. All right, so it looks like this was released in 1995, but then they decided to obsolete this original one and write a new one. So let's read about why they decided to do that. There are numerous editorial changes in comparison with RFC 1771. Too many to list here. The following list the technical changes. Changes to reflect the usage of features such as TCP MD5, BGP route reflectors, BGP confederations, and BGP route refresh. So when they wrote the original one, they didn't know about any of that, so they decided to rewrite and include that as part of it. Clarification of the use of the BGP identifier in the aggregator attribute. Procedures for imposing an upper bound on the number of prefixes that a BGP speaker would accept from a peer. Now, I'm surprised that they would want to do that, because I thought the point of BGP was for it to be as scalable as possible. So an upper bound seems kind of counterintuitive to me. And it kind of basically, like, the first thing you would want to do if there were an upper bound is to have a different protocol that allows you to break that upper bound. So a BGP speaker may support the ability to impose a locally configured upper bound on the number of prefixes the speaker is willing to accept from the neighbor. Okay, that makes a lot of sense. So you can say, okay, I've got this device. It's got this amount of CPU memory. So if I put 2 million BGP routes on it, it's going to tank the device. So I'm going to set the upper bound to 1 million because I know my device can handle that. And even though BGP can scale up and allow for more than that, I can basically put a safety check in it and say, no, you're not going to tank my router by just sending me millions more routes than my router can handle. I'm setting this upper bound on there, and that will prevent you from crashing my gear. So that makes a lot of sense to me. The ability of a BGP speaker to include more than one instance of its own AS in the AS path attribute for the purpose of inter-AS traffic engineering. Classification of the various types of next hops. Clarification of the various types of next hops. So I guess they didn't have that clarified very well before. So let's look at that again, because I guess I don't know what different kinds of net hops there are. That doesn't really ring a bell for me. So looks like we got 59 mentions of that. So maybe it's covered. Okay, so far I don't see anything about types of next hops. Yeah, I don't see anything about the types of next hops, so I'm not sure where that clarification was made. I mean, it's probably made under here, right? Here's how it's calculated. Steps 1, 2. It's calculated in 3 steps. I guess maybe this is where they're doing it. All right. Well, let's just move on. Yeah, I guess I'm not sure what they mean by this clarification of the various types of next hops. I don't see where they did that. I can see that they're showing how it's calculated, so maybe that's here, but I don't see anything about the different types of them. I just see how it's calculated. Like, I don't see a list of next hop types. Huh. All right. Clarification of the use of the atomic aggregate attributes. The relationship between the immediate next hop and the next hop as specified in the next hop path attributes. Clarification of the tie-breaking procedures. Clarification of the frequency of route advertisements. Optional parameter type 1 authentication information has been deprecated. Update message error subcode 7 AS routing loop has been deprecated. Open message error subcode 5 authentication failure has been deprecated. Use of the marker field for authentication has been deprecated. Implementations must support TCP MD5 for authentication. Clarification of Bgpf SM. Appendix B, comparison with RFC 1267. Let's take a look at that. Oh, okay. So this is BGP version 3. See, years and years ago. This is from 1991, but this one's from 2006. So, I mean, basically 2005. It's the beginning of 2006. So, all right, but let's see how it's different from version 3. We had more than 10 years to make improvements. All the changes listed in Appendix A, plus the following. Bgp-4 is capable of operating in an environment where a set of reachable destinations may be expressed via a single IP prefix. The concept of network classes, or subnetting, is foreign to Bgp-4. To accommodate these capabilities, Bgp-4 changes the semantics and encoding associated with the AS path attributes. New text has been added to define semantics associated with IP prefixes. These abilities allow Bgp-4 to support the proposed supernetting scheme. Oh, I'm surprised I can't click on 18. Yeah, so this is a big one. This is a proposed standard again. It's so weird. I don't understand. But it's the standards track categories. So now that's the category. So is it going to be under? Now this is status. How do I look at it by category? It should be under here, right? So this is 1519. I'm just trying to get a sense for which. I mean, I guess I'm going to do them all, right? So if I can. I mean, there's just so much to read. I doubt I even have time to read all of this in a lifetime. But yeah, so I just want to get the most bang for my buck as I'm working through these. I think the best way to do that is to pick out kind of which one has been. I'm gonna skip all the historic ones because this is where you get like. But at the same time. Oh, this is not. I thought this was a VoIP protocol, but yeah, like these are not. These I can definitely skip. Yeah, these are historic. We probably got RFC 69 in here as well. Oh! I mean, I definitely want to skip all the RFCs that are categorized the same as RFC 69. But I'm just wondering if RFC 699 Alright, so let's continue on. To simplify configuration, this version includes a new attribute, local pref, that facilitates route selection procedures. The inter-AS metric attribute has been renamed multi-exit discriminator. Oh, I kind of like that original name a little bit better. A new attribute, atomic aggregate, has been introduced to ensure that certain aggregates are not de-aggregated. Another new attribute, aggregator, can be added to aggregate routes to advertise which AS and which BGP speaker within that AS caused the aggregation. To ensure that hold timers are symmetric, the hold timer is now negotiated on a per connection basis. Hold timers of 0 are now supported. Comparison with RFC 1163, let's take a look at that. So this looks like it's even earlier, it's from 1990, and this looks like the original version of BGP. So like version 1, I guess I'm not sure what happened to version 2, but all of the changes listed in Appendixes A and B, plus the following: to detect and recover from BGP connection collision, a new field, Bgp identifier, has been added to the open message so that it can choose the lowest identifier for the collision. And we can see a collision in the lab. That's just real easy. So if I start a capture, that's probably one of the easier things to take a look at is the collision. And then I'm going to filter this out for BGP. There we go. Now you can see our connection is happy. So let's mess things up a bit. Let's get devious. There we go. So CLI, whoops, CLI, configure private, deactivate interface 0 to 0. We want to do 0 or do I want to do 1? Let's deactivate 1. There we go. Commit. There we go, and we should get a disconnect message. Unless it was already deactivated. Oh! Okay, yeah, I want to disable it, not deactivate the configuration on it, because even though there's no active configuration on it, the port's still going to be up. In order to actually bring it down, I've got to disable the port, I believe. Okay, so now the port is actually down. Oh, was it down before though? I think I was checking the wrong port. No, it was up before. Okay, but that's fine. Let's shut down 0 as well. Okay, so now we should see a notification message. I think, or not. I guess we're not going to see that. Oh, you know what? I'm just the reason we didn't see anything special on the other side is because there's 2 links to sniff. So we would have saw something interesting if I were sniffing this link, but I'm only sniffing this top link. And the reason we're not seeing anything right now is because the hold timer hasn't expired. So let's take a look at Bgp Summary. Okay, so we still got a hold timer. Neighbor. So, okay, so yep, so our hold time is 90 seconds. That's quite a long time. But it looks like we did get a cease. So it's going to send that out. It should send a few more, because I think if it doesn't receive 3. Okay, so let's watch this here. Yep, so we've got our time ticking. Still only have 1 cease event, but we do have our hold time set to 90, which is pretty high. I should probably reconfigure that, set that down lower. If I want to watch these, analyze these, I definitely want to. So we've got a flag here, pure interface error. And I'm not sure why that is the case, because it's this interface that's shut down. But we gotta wait for this hold time to expire. Aha! So now we've got a notification. Hold time did expire now, so we should see it. Oh, you know what? That was the last state. Ah, here we go. Perfect. So now we're in idle. We still only have 1 cease sent, but the hold timer has now expired. All right, so let's take a look at that race condition. Okay, so now we've got our open messages, but you can see we've got two of them. We've got an open message sourced from .2 and an open message sourced by .1. So we're going to get a notification message. Here it is, and this will have a. We're actually going to get another notification message. I don't think it. I think something happened on the other side. Like it didn't completely time out on the other side. Okay, we're getting our keep alives now, so I'm not sure what's going on here. This isn't what I was expecting. Yeah, because now we're getting keep alive messages from both sides. You know what? Let me just set the hold timer. Set it down to 5 seconds. Now this should drop the connection. We should get an error because the hold timer is not set correctly. Yep. So we got a notification message. We're resetting. So we got to wait for the old hold timer value to expire, though. Oh, actually, it looks like we're good. All right, let's change the hold time to 5 seconds on this side. Oh. Protocols BGP group internal hold time 5. All right, and that's 5 seconds. Okay, so we got a hard reset, I bet, again. Yep. The hold time should be showing up somewhere, right? Nah, I don't think so. I don't think the hold time shows up anywhere. Yeah, it's the FSM, finite state machine. So it's like it's on the device. It's not like the local device doesn't send anything out to other devices because it's not, the hold timer isn't meant to be shared. All right, but let's see that hold time expire much more quick now. Okay, so after 5 seconds, it's going to expire. There we go. We've already got a hold timer message. Real fast. Real fast this time. Real fast. Okay, and now we don't have any more traffic because it is down. It has expired on both sides. So let's roll that back and see what happens now. Okay, now we got 2 open messages again. We should have a notification message. We should have a cease. See, I don't get why there's no cease. I'm confused. Does it only happen for... Oh no, here it is, here it is. Yeah, this is the cease. So now, no, because it should say collision. It should say that it's for a collision. Okay, I don't understand. Yeah, I was expecting this message to say that it was for a collision. Alright, well that isn't exactly how I had envisioned it going. And I don't know why. Maybe because it's eBGP. Let's try it as iBGP. Because if it's eBGP, maybe it just uses the AS or something. Yeah, because it has different ASs, so it can choose the higher or lower AS. But if it's iBGP, it doesn't have that. So let's try it as iBGP. Okay, so to do that, we just need to change the type to internal. Then we're not going to need a pure AS anymore. All right, and then we need the local ASs to match. All right, but that's all there is to it. On router 2, we also need to make some changes on router 1. We're going to need to change the type to internal. We're going to need to delete the pure AS. We don't need to supply that information anymore. We know it's going to be the same as our local AS. But that's it. We need to do one less change here because our local AS is already correct. Alright, aha, and now we can see Wireshark knows that it's iBGP and it colors it in tan instead of red, which it uses for eBGP. Oh, so we got a bad pure AS message here. I'm not sure what that's all about. I think my pure AS is fine. Let's just take a look at what I've got on here. So we've got a local AS is 1. Local AS is 1. So I don't see what the complaint is. Looks like there's no complaint. We've got keep alive messages. Alright, so let's see if we can get that race condition now. I don't see it before, but we'll try it. Okay, so hold timer should expire in 5 seconds. There we go. Nice and snappy. Hold timer expired. Alright, so let's see what happens if I roll this back. Do we get a collision notification message? We do not get a collision. Yeah, that's weird. I don't know why we don't get a collision. I thought you always got one. Unless you made one side passive. I'm confused. I guess let me try this. instead of shutting down the port, let's deactivate the BGP configuration. Okay, so now it's going to be a little bit different since we're specifically cutting off BGP and we're not cutting off TCP entirely. It still has a TCP connection. So we've got the hard reset, and we've got no more chatter on the line. So let's see what happens now that it is severed in a different way. How does it reform now? Okay, so we got our open message. We should have a notification. Don't have one. Another open message. Keep alive, update. Yeah, I'm confused. I don't understand why I'm not seeing that collision message anymore. Yeah, that's really confusing. I don't understand. I don't understand at all. Not even a little bit. All right, well, let's just move on then and try to get through the rest of the RFC. I guess what I can do is close the capture. Oh, was I capturing the wrong? No, I was capturing 0. Wait, where was I? Oh, I think I was here. Yeah. Oh, or was I here? I definitely finished this. So I think I'm here. So let me continue. All the changes listed in Appendices A and B plus the following to detect and recover from BGP connection collision. A new field, Bgp identifier, has been added to the open message. New text 6.8 has been added to specify the procedure for detecting and recovering from collision. The new document no longer restricts the router that is passed in the next hop path attribute to be part of the same autonomous system as the BGP speaker. The new document optimizes and simplifies the exchange of information about previously reachable routes. Okay, so let's go back and look at this. So if a pair of BGP speakers try to establish a BGP connection with each other simultaneously, then 2 parallel connections will be formed. And it looks like they did try to do that. Like I saw the 2 open messages being sent. If the source IP address used by one of these connections is the same as the destination IP address used by the other, and the destination IP address used by the first connection is the same as the source IP address used by the other, connection collision has occurred. Aha! So that's what's going on, I think. We've got, so I can get rid of this link here, that's shut down anyway. We've got a source IP address different. I think router 2 was using maybe the 9.9.9 or something from the loopback for its source IP address. So I think that's what was happening. So let's make sure that it's using a source that is going to cause a collision, and then we'll cause the collision. So first, let's just prove that everything is that there is going to be no collision, and we'll take a look at the source and the destination IP addresses. So let's do set interface disable, commit. Okay, we'll do a show configuration, pipe display set, pipe no more. Okay. So here's our notification for shutting that down. Hold timer expires since it's set to 5 seconds now. So we're going to roll this back, and we won't get a collision because the source IP, because we'll see why. We'll see why we won't get a collision. So yep, we can see we don't have a notification message. Everything is hunky-dory, no problems there. So if I do a show BGP summary, we can see our peer is 10.10.10.2. Now let's take a look at this side. Oh, here's a notification message. Other configuration change. What does that mean? It should say collision. Yeah, I mean, it looks like it is meeting the criteria. But you know what? I think the source. Let me do this. So BGP neighbor.2. Here we go. So the local is 10.10.10.1. So let's see what the other side says. I'm expecting the local to be something else. Okay, that's interesting. The local is 10.10.10.2. So we can see it does meet the criteria in the RFC for triggering a collision. They're trying to establish it simultaneously, and the source IP used by one is the same as the destination used by the other. So here on router 1, the source IP is local here, 10.10.10.1. That's the same as the peer if we go to router 2, 10.10.10.1. Likewise, the source on router 2, 10.10.10.2, that's the same as the peer on router 1, 10.10.10.2. So there should be a collision. I don't know why it's not showing up. Is it because the peer ID? Yeah, maybe it's because the peer ID. But the thing is, it looks like it didn't close one of the connections because it sent two BGP open messages. Oh, stop scrolling. Draw packets using. Okay, yeah, there we go. So where did this all happen? It all happened right here. Yeah, so we've got two open messages, one sourcing from .2, one sourcing from .1. So one of these should back off, but I didn't see that happening. I guess it does happen here. It looks like .1 backs off, so that means initiated from .2 will be the one that's actually live. So that means that the peer for .2 will have 179. Let's see if that's the case. Yep. So that is the case. But it looks like the back off message showed up as other configuration change instead of as collision. That's surprising. Yeah, it should. Yeah, it's accomplished by sending the notification message with the error code cease. Yep. Okay. So this is the collision message. I'm just surprised it didn't say collision. I think sometimes it does. So I'm not sure what's going on with that. But we can see it did send a notification message with the error code cease. So it is compliant with what we read about here in the RFC. All right. So comparison with RFC 1105, which is an even older version, 1989 of the original BGP protocol. All of the changes in appendices A, B, and C, plus the following: minor changes to the RFC 1105 finite state machine where necessary to accommodate the TCP user interface provided by BSD version 4.3. The notion of up-down horizontal relations presented in RFC 1105 has been removed from the protocol. Changes in the message format from RFC 1105 are as follows. Number 1, the hold time field has been removed from the BGP header and added to the open message. Number 2, the version field has been removed from the BGP header and added to the open message. Number 3, the link type field has been removed from the open message. 4, the open confirm message has been eliminated and replaced with implicit confirmation provided by the keep alive message. Number 5, the format of the update message has been changed significantly. New fields were added to the update message to support multiple path attributes. 6, the marker field has been expanded and its role broadened to support authentication. Note that quite often BGP, as specified in RFC 1105, is referred to as BGP-1. BGP, as specified in 1163, is referred to as BGP-2. BGP, as specified in 1267, is referred to as BGP-3, and BGP, as referred to in this document, is referred to as BGP-4. Okay, so there's the answer to my question, what happened to BGP-2? It is 1163, obsoleted by BGP-3, which is obsoleted by BGP- wait, what? Is it? Well, that's weird. It looks like this hasn't been obsoleted by -4, which I guess makes sense. Like maybe you can choose to use -3 or -4. So -4 doesn't actually obsolete -3. But I guess I'm surprised that it wouldn't. Like I would think that -4 would obsolete -3, but perhaps that's not the case. So I guess that's something you gotta be aware of is your networking gear using -3 or -4, because it looks like -4 did not obsolete -3, so even though you might think you have BGP on your networking gear, it might actually turn out to be -3, which doesn't get you everything you need. So, all right, Appendix E, TCP options that may be used with BGP. If a local system TCP user interface supports the TCP push function, then each BGP message should be transmitted with push flag set. Setting push flag forces BGP messages to be transmitted to the receiver promptly. If a local system TCP user interface supports setting the DSCP field, RFC 2474 for TCP connections, then the TCP connection used by BGP should be opened with bits 0 through 2 of the DSCP field set to 110 in binary. An implementation must support the TCP MD5 option. Implementation recommendations. This section presents some implementation recommendations. The first recommendation is multiple networks per message. The BGP protocol allows for multiple address prefixes with the same BGP attributes to be specified in one message. Using this capability is highly recommended. With one address prefix per message, there is a substantial increase in overhead in the receiver. Not only does the system overhead increase due to the reception of multiple messages, but the overhead of scanning the routing table for updates to BGP messages and other routing protocols and sending the associated messages is incurred multiple times as well. One method of building messages that contain many address prefixes per path attribute set from a routing table that is not organized on a per path attribute set basis is to build many messages as the routing table is scanned. As each address prefix is processed, a message for the associated set of path attributes is allocated. if it does not exist and a new address prefix is added to it. If such a message exists, the new address prefix is appended to it. If the message lacks the space to hold the new address prefix, it is transmitted, a new message is allocated, and the new address prefix is inserted into the new message. When the entire routing table has been scanned, all allocated messages are sent and their resources are released. Maximum compression is achieved when all destinations covered by the address prefixes share a common set of path attributes, making it possible to send many address prefixes in one 496-byte message. When peering with a BGP implementation that does not compress multiple address prefixes into one message, it may be necessary to take steps to reduce the overhead from the flood of data received when a peer is acquired or when a significant network topology change occurs. One method of doing this is to limit the rate of updates. This will eliminate the redundant scanning of the routing table to provide flash updates for BGP peers and other routing protocols. A disadvantage of this approach is that it increases the propagation latency of routing information. By choosing a minimum flash update interval that is not much greater than the time it takes to process the multiple messages, this latency should be minimized. A better method would be to read all received messages before sending updates. Another implementation recommendation is reducing route flapping. To avoid excessive route flapping, a BGP speaker that needs to withdraw a destination and send an update about a more specific or less specific route should combine them into the same update message. Another implementation recommendation is path attribute ordering. Implementations that combine update messages, as described above in section 6.1, may prefer to see all path attributes presented in a known order. This permits them to quickly identify sets of attributes from different update messages that are semantically identical. To facilitate this, it is useful optimization to order the path attributes according to type code. This optimization is entirely optional. Another thing to consider when implementing BGP is AS set sorting. Another useful optimization that can be done to simplify this situation is to sort the AS numbers found in an AS set. This optimization is entirely optional. Control over version negotiation. Because BGP-4 is capable of carrying aggregated routes that cannot be properly represented in BGP-3, an implementation that supports BGP-4 and another BGP version should provide the capability to only speak BGP-4 on a peer-to-peer basis. Appendix F.6, complex AS path aggregation. An implementation that chooses to provide a path aggregation algorithm retaining significant amounts of path information may wish to use the following procedure. For the purpose of aggregating AS path attributes of two routes, we model each AS as a tuple type value, where type identifies a type of the path segment the AS belongs to, for example, AS sequence, AS set, and value is the AS number. Two ASs are said to be the same if their corresponding type value tuples are the same. The algorithm to aggregate two AS path attributes works as follows. A. Identify the same ASs as defined above within each AS path attribute that are in the same relative order within both AS path attributes. Two ASs X and Y are said to be in the same order if either X precedes Y in both AS path attributes or Y precedes X in both AS path attributes. The second step of the algorithm, B, the aggregated AS path attribute consists of ASs identified in A in exactly the same order as they appear in the AS path attributes to be aggregated. If two consecutive ASs identified in A do not immediately follow each other in both of the AS path attributes to be aggregated, then the intervening ASs that are between the two consecutive ASs that are the same in both attributes are combined into an AS set path segment that consists of the intervening ASs from both AS path attributes. This segment is then placed between the two consecutive ASs identified in A of the aggregated attributes. If two consecutive ASs identified in A immediately follow each other in one attribute, but do not follow in another, then the intervening ASs of the latter are combined into an AS set path segment. This segment is then placed between two consecutive ASs identified in A of the aggregated attribute. And the last step of the algorithm to aggregate two AS path attributes is for each pair of adjacent tuples in the aggregated AS path, if both tuples have the same type, merge them together if doing so will not cause a segment of a length greater than 255, so 1 octet, to be generated. If, as a result of the above procedure, a given AS number appears more than once within the aggregated AS path attribute, all but the last instance, rightmost occurrence, of that AS number should be removed from the aggregated AS path attributes. Okay, so we've got some security concerns here. So it looks like we only got 2 pages left to read, or about 3 pages left, 2.5 pages to read. So let's finish this out with some security concerns here. Considerations. A BGP implementation must support the authentication mechanism specified in RFC 2385, which I'm sure is MD5 authentication. Yep. So let's set that up quick, because that's standard. It must be on all of them. So let's refresh our memory here. We're going to do edit protocols, BGP group internal, set authentication. I'm going to do algorithm. Now we've got additional kinds that are even more secure, but the ones that must be included in every implementation are the MD5. So let's just go with that one. That's good enough for now. And now we're going to set a authentication key as well. So we'll say very secure will be our password. Okay, now when I commit that, we're going to see it go down, and then we're going to get a notification message because the password has not been set up on both sides. Oh, I can't configure it with a key. Oh, I've got a key still. Why can't I use a key? Did I get a notification? No, I didn't. Now, why can't authentication algorithm MD5 may not be configured with authentication key? Alright, well, let's try removing the authentication algorithm MD5 then. Okay, now we've got a notification message because we don't have it set up on the other side. We've got a cease code here. But what I'm confused about is... Oh, okay, so it looks like it is an MD5 if I use that key. But I don't get why... Do I... Oh, I see, because I think I have to include it on the... like this. Yeah. So let me do a rollback 1. Or let's do a rollback 0, then a rollback 1, and a show pipe compare. There we go. So now we're getting rid of the key command. We'll do edit protocols, BGP group internal, show pipe display set relative. Okay, and now we'll do set authentication algorithm MD5, authentication key, very secure. Now this should work. Oh! Still doesn't work. Yeah, I don't know why I can't configure a authentication key if I configure a authentication algorithm. That doesn't make any sense. Now, can I configure a authentication keychain with an authentication algorithm? And then if I edit or set key protocols BGP group internal authentication key chain test key set firewall set policy options. Where do I set up a keychain? help star match help match key chain. Oh, I completely broke everything. Oh, here we go. Edit security authentication keychain. Oh. Okay, it looks like my clear. Delete. What is it? It's, oh yeah, we have request. Request. Session. Or request system configuration. Request system logout user or PID, yeah. Show system user, yeah. So I've got a user. Or show system processes. There we go. So now we've got wait, brief. Because there's a oh, you know what? It tells you. If I configure private, there you go. It gives you the PID right here. There we go. So now if I go back, I killed all those changes, no longer there. And now I can make edit security authentication keychains. We'll say my key chain. Oh, keychain, my chain. I'm gonna do set key. I'm gonna have name key 0, and we'll say algorithm MD5, and I'm gonna do secret very secure, and we'll do start time. Run show system uptime. Okay, so start time, key 0, start time, current time. Go. Date. Dot. Hours. Oh, yeah. So we'll start at 05. Perfect. Okay, and then we'll do edit protocols, BGP group internal, show pipe display set relative, set authentication algorithm MD5, set authentication key chain, my key. Okay, so let's see if I can do it this way. So I think if you set the authentication algorithm, you have to use a keychain. But let's see if that theory is true. That is, okay. So yeah, if you set the algorithm to MD5, you've got to use a keychain. You can no longer just use a base MD5 password without it being a keychain, and that's because the keychain actually has the algorithm in it you can set. You don't have that when you just set it on you just set it basic. So that was good to know. I actually didn't know that. So just for a quick review again. Oh, and we can see we've got a notification message because we don't have a keychain set up on the other side. So you know what? Let's do that. We're gonna do run. We're gonna do show pipe display set pipe match key. Okay, and now we've got everything here. So let's set it up on the other side and have that come back up. There we go. So now we should have an open message, hopefully, or not. We're not going to have an open message? I don't think we're going to have an open message. Well, why the heck not? So we've got the interface up, we can ping it. Oh, wait, we're still inactive here. Oh, you know what? We've got a different algorithm on this side. Not sure how that happened. Yep, here we're using MD5 algorithm, but here we're using this HMAC algorithm. Which is interesting because you can see we've got the algorithm specified. But you can see here we're missing a command. We've got the keychain, but we don't have the algorithm. That's really bizarre because we do have the algorithm in the keychain, but I guess that is overwritten by the algorithm specified in the actual BGP group, and by default it uses this algorithm here. Because if I look at the keychain config, you can see we do have algorithm MD5, but you can see we are missing the algorithm command here. So it looks like the default algorithm is here, and that overwrites the algorithm specified in the keychain. All right, so let's set up the correct algorithm. which is MD5. Okay, and we should see the open messages being sent out now on our Wireshark capture. Okay, I do see it, Perfect. And we should get a notification soon because there's that race condition. I don't have a passive setup, and I've got the source and destination IPs on the same, they're matching on the same subnet. Should get that pretty soon here. Sometimes it takes a little bit of time for one side to back off. Interesting, I don't see it. I do not see that message. That is interesting. Why don't I see it? Maybe I got it early? No, I just legitimately haven't received it yet. Okay. Guess I just haven't received it. Yeah, that's kind of different. I'm not sure why that is so different. But to further drive things home, I'm gonna set the keychain algorithm to something else, and then we'll see that even though I set the keychain algorithm to HMAC SHA1 and committed it, okay, it looks like I actually can't set it to something else. The only option is, I mean, I guess I can delete it. Let me just delete it and see what the default is. It's probably MD5. Okay, so this should set it to the default. Let's see what happens. There we go. So now we can see there is no algorithm specified. So let's do a show security authentication or security keychain. Detail. So now we've got the algorithm set to HMAC MD5, but we should see BGP neighbor 10.10.10.2. The algorithm is MD5. So yep, it looks like it's still overwrote the algorithm on here because we can see if the default is HMAC MD5. So let's set it back. So I'll do a rollback 1, show pipe compare. We're going to set it to MD5, so we should see that change from HMAC MD5 to MD5. And we should see the connection. And the connection's not going to go down or anything because even though we're changing the algorithm on the keychain, the algorithm for the BGP neighbor specified in the group overwrites whatever is. It basically just ignores what's in the keychain, but it probably doesn't if you don't have it specified in there. Then it probably goes with what's in the actual keychain. Oops, I am on a Linux machine. I'm on a FreeBSD machine here, but this is Junos OS running on that. So unless I do start shell, I can do an ls there, but here I'm running a program. I'm running the Junos OS. So, right, let's take a look at the keychain again. Show security keychain, detail. So yeah, we can see that HMAC is the same as MD5 pretty much. Yep, so now we are defining the algorithm to MD5, but it's still HMAC. MD5, that's the same thing. And then of course we're going to have no changes to our neighbor because we never actually changed the algorithm at all. Okay, let's see what happens when I delete this. Okay, so it deletes successfully. Now, are we getting a notification? We are getting a notification here. And that's because the whole timer has expired, set to 5 seconds, so it happens really quick. And I'm betting the authentication no longer matches. I'm betting it's now HMAC instead of HMAC MD5 instead of MD5. Oh, so it looks like, aha, so yep, that's right. And I remember this from before. When you get rid of the authentication algorithm, it still overwrites what's in that keychain, but it does it with a default algorithm. Even though you don't have that command anymore, by default it goes with this. So basically having that added to your keychain is just kind of a waste of a command. Not necessary at all. You can just leave it out, go with the default, and it will just overwrite it with. But where you do want to make sure you have it specified is in the BGP protocols, BGP group internal set authentication algorithm MD5. You want to make sure it's there, otherwise by default it will use, or it could potentially use the SHA algorithm. Okay, so now we've got the MD5 algorithm. And alternatively, what you could do is not use keychains, but then you don't get extra options like starting your keychain at a specific time, using different passwords in sequence, so you don't get quite as secure authentication options not using a keychain as you do with keychains. Keychains gives you a lot of extra features that can make your network a lot more secure. So just setting it up using a basic keychain, basically just as if you would set it up if you weren't using keychains at all, just with a few extra configuration steps, is probably worth it, because if you do need that extra security, it'll be easier to add it once you're already used to using keychains. But I will go over the difference between a more simple setup that does not use keychains. Okay, so in order to not use a keychain, first step is of course going to be deleting the call of the actual keychain. Okay, so now we're no longer bringing in the keychain that we have defined. Next thing we're going to do is get rid of the actual definition of the keychain. Now, this doesn't matter too much to do because it's no longer being called, so we could just leave it on there, but it's kind of junky. Since it doesn't do anything, we'll get rid of it and make the candidate configuration look a lot better. And then when we commit that, it'll go into the active configuration, and that'll look better too. We've got an A here because it wrapped, so this is part of the secret data comment. So we can see we no longer have our keychain, and we no longer call our keychain in. But if I do a commit check, it's going to fail because what? What the hell? I thought you couldn't. Oh, you know what? It's going to succeed, but I can't set up authentication now unless I use a keychain. So if I try to do set protocols BGP group authentication group internal authentication key, and then just give it a password very secure, and then do a commit check. Now it's going to fail because I didn't use a keychain. So if I want to do it that way without using a keychain, I've got to delete the authentication algorithm. Oops. Okay, so now that I have the authentication algorithm deleted, you can see I'm still adding that key on there. So if I do a commit check, there we go, commit check succeeds. So let's commit and quit. And then we'll go over to router 2. We'll get our hold timer expiring. There we go, hold timer expired. Do a show pipe, show configuration, pipe display set, pipe no more, configure private, delete security, delete protocols BGP group internal authentication algorithm and authentication keychain. Okay, and then we'll set internal authentication key, very secure. And there you go. That's the simplest way to set up MD5 authentication on your router. If we go back to the output, show BGP. There we go. We've got our open message back. Neighbor 10.10.10.1. Oh, it looks like we're still building up that connection. Oh, we got some notification messages as well. So, oh, here we go. Now we got the actual connection collision resolution. I was expecting to see this before. I don't know why we hadn't been seeing that. I don't know why this is the first time we've seen that. That's interesting. That's not what I expected. But we can see it resolved itself. Yeah, I don't know why that message has been hidden, but yeah, I'm kind of confused now. I don't understand what's going on. But let's take a look at our authentication here. So we've got an authentication key configured. So those are two very different things. Let's compare them side by side. We can do that more easily here. So let's take the first output, and we'll do it from the MD5. Yep, this looks good. All right, and then we'll put that next to this output. So we can see here we've got authentication keychain and authentication algorithm, but here we just have an authentication key. So those are two completely different things. We've got auth keychain is the option, but here we just have auth key. Two completely different ways to configure authentication. Yeah, I'm not sure if, like, on the JNCI ESP, like, I mean, obviously, again, I'm under a do not disclose agreement. I can't talk about anything I saw in the test at all. But I can certainly talk about the publicly posted curriculum. So let's look that up again, and let's see if there's a distinction between the two kinds of authentication. So this would be under BGP, and it would be under it would be here. Yeah, I don't see any kind of, so it would be under here, BGP adjacency formation. But I don't see anything more specific than that. But it would definitely be here. We can see we do have authentication for IGPs, but we don't have anything more clear about what kind of authentication would be on the test. Keychain authentication, or off keychain or off key. So we just have to read the instructions carefully and make sure to do what the instructions are calling for, which is the hardest part of any test, really. Okay, let's try to finish this tonight. Security considerations. A BGP implementation must support the authentication mechanism specified in RFC 2385. So this is protection of BGP sessions via the TCP MD5 signature option. So this looks like that option that doesn't use keychains. Let's see if the word chain shows up here. Nope. So yeah, this is the part that doesn't use keychains. So they must support that, but it looks like Junipers have extra features. It allows for keychains as well, in addition to RFC 2385 off-key authentication. It also allows for off-key chain authentication, which gives you some extra features. The authentication provided by this mechanism could be done on a per peer basis. BGP makes use of TCP for reliable transport of its traffic between peer routers to provide connection-oriented integrity and data origin authentication on a point-to-point basis. BGP specifies use of the mechanism defined in RFC 2385, which is protection of BGP sessions via the TCP MD5 signature option, same one up here. These services are intended to detect and reject active wiretapping attacks against the inter-router TCP connections. Absent the use of mechanisms that affect these security services, attackers can disrupt these TCP connections and/or masquerade as a legitimate peer router. Because the mechanism defined in the RFC does not provide peer entity authentication, these connections may be subject to some forms of replay attacks that will not be detected at the TCP layer. Such attacks might result in delivery from TCP of broken or spoofed BGP messages. The mechanism defined in RFC 2385 augments the normal TCP checksum with a 16-byte message authentication code, MAC, that is computed over the same data as the TCP checksum. This MAC is based on a one-way hash function, MD5, and use of a secret key. The key is shared between peer routers and is used to generate MAC values that are not readily computed by an attacker who does not have access to the key. A compliant implementation must support this mechanism and must allow a network administrator to activate it on a per-peer basis. RFC 2385 does not specify a means of managing, for example, generating, distributing, and placing The keys used to compute the MAC. RFC 3562, an informational document, provides some guidance in this area and provides rationale to support this guidance. It notes that a distinct key should be used for communication with each protected peer. If the same key is used for multiple peers, the offered security services may be degraded, for example, due to an increased risk of compromise at one router that adversely affects other routers. The keys used for MAC computation should be changed periodically to minimize the impact of a key compromise or a successful cryptanalytic attack. RFC 3562 suggests a crypto period, an interval during which a key is employed, of at most 90 days. More frequent key changes reduce the likelihood that replay attacks, as described above, will be feasible. However, absent a standard mechanism for effecting such changes in a coordinated fashion between peers, one cannot assume that BGP-4 implementations complying with this RFC will support frequent key changes. Obviously, each should key also be chosen to be difficult for an attacker to guess. I think they mean each key should. I'm not sure what a should key is. The techniques specified in RFC 1750 for random number generation provide a guide for generation of values that could be used as keys. RFC 2385 calls for implementations to support keys composed of a string of printable ASCII of 80 bytes or less. RFC 3562 suggests keys used in this context to be 12 to 24 bytes of random pseudorandom bits. This is fairly consistent with suggestions for analogous MAC algorithms, which typically employ keys in the range of 16 to 20 bytes. To provide enough random bits at the low end of this range, RFC 3562 also observes that a typical ASCII-2 text string would have to be close to the upper bound for the key length specified in RFC 2385. Bgp Vulnerabilities Analysis is discussed in RFC 4272. Yeah, this looks super interesting. It's informational. This looks really interesting. It sounds really vulnerable. Yeah, so here's where if you use keychains instead of just the key on there, you can implement some of these practices automatically just by setting up like rotating keychains all at once. You make it a bit a lot more secure just up front without having to go back into the device and every 90 days configuring a new key. You can just set it up for every 90 days until the end of time, pretty much. You can probably send up 10 keys, or for at the end of every year you go and you give it more keys. Much better way to do it. Okay, so we've got 2 pages left before I'm completely done. I kind of want to, you know what, I'm going to pause it and get some water, come back, and then I'll close this out. Alright, so last section is Iana Considerations. All the BGP messages contain an 8-bit message type for which Iana has created and is maintaining a registry entitled BGP Message Types. This document defines the following message types: open, which is type 1, update, type 2, notification, 3, keep alive, 4. Future assignments are to be made using either the standards action process defined in RFC 2434 or an early Iana allocation process defined in RFC 4020. Assignments consist of a name and a value. The BGP update messages may carry one or more path attributes, where each attribute contains an 8-bit attribute type code. Iana is already maintaining such a registry called Bgp Path Attributes. This document defines the following path attributes type codes. So, yep, this all looks really familiar, as well as these. These are the message types. We've got 4 message types. We've also got path attributes. We've got 7 types of those. The origin, which is type 1. The AS path. It's value 1. AS path is 2. Next hop 3. Multi-exit discriminator 4. Local pref 5. Atomic aggregate 6. And aggregator 7. Future assignments are to be made using either the standards action process defined in RFC 2434 or the early Iana allocation process defined in RFC 4020. Assignments consist of a name and a value. BGP notification message carries an 8-bit error code for which Iana has created and is maintaining a registry entitled BGP error codes. This document defines the following error codes. Error code 1 for notification messages is message header error. 2 is open message error. 3 is update message error. 4 is whole timer expired. We saw that when the whole timer expired. Value 5 is finite state machine. And we also saw value 6, cease, when it took care of the fact that there were open messages sent from each router, and the source matched the destination respectively on each router. Future assignments are to be made using either the standards action process defined in RFC 2434 or the early Iana allocation process defined in RFC 4020. Assignments consist of a name and the value. BGP notification message carries an 8-bit error subcode where each subcode has to be defined within the context of a particular error code and thus has to be unique only within that context. Iana has created and is maintaining a set of registries, error subcodes, with a separate registry for each BGP error code. Future assignments are to be made using either the standards action process defined in RFC 2434 or the early Iana allocation process defined in RFC 4020 as the other things, as is true of the other ones as well. Assignments consist of a name and a value. This document describes the following message header error subcodes. Number 1, connection not synchronized. Number 2, bad message length. Number 3, bad message type. This document describes the following open message error subcodes. Number 1, unsupported version number. Number 2, bad pure AS. We saw that one when I was changing the ASs. Number 3, bad BGP identifier. 4, unsupported optional parameter. 5 is deprecated. 6, unacceptable hold time. This document defines the following update message error subcodes. Number 1, malformed attribute list. Number 2, unrecognized well-known attribute. Number 3, missing well-known attribute. Number 4, attribute flags error. Number 5, attribute length error. Number 6, invalid origin attribute. Number 7, deprecated. Number 8, invalid next hop attribute. Number 9, optional attribute error. Number 10, invalid network field. And number 11, malformed AS path. All right, I did it. I read not every word. I'm not going to read this. I mean, I skimmed it, but I read pretty much every single word in the most current draft standard for BGP version 4, and I even submitted to the errata and got my submission approved. So I say when it comes to BGP, I am definitely learned on it. There's no doubt about that. So yeah, I guess I'm feeling a little bit better about myself. I was feeling pretty down on myself after I took the JNCI ESP. I was expecting myself to be more I was expecting that to be one of my strongest subjects, and it didn't turn out to be. So I wanted to do this just to make sure there were any gaps or holes in my knowledge were filled in, and sure enough, I had a big gap when it came to MED, and yeah, so this filled that in really good. So yeah, thanks for coming along with me on this journey. It was quite a journey. I might take this series in a new direction now, and focus on design guides from vendors. Alternatively, I could keep reading RFCs, focusing on standards, standards track, and just going by newest to oldest, or just like picking out the OSPF one, or just whatever I choose to do. Yeah, I'm gonna keep contributing to this series. But now that I'm done with the BGP RFC, we'll see what comes next. So thanks for watching, and it's kind of anticlimactic, but yeah, I read the whole RFC. I don't know why I did that. I don't know what I expected to get out of it, but I certainly did, at the very least, get out a much better understanding of MEDs. So thanks for watching, and see you in another video.